Yes, if you have any question, you can ask.
Yeah, so I have a doubt from an assignment, from assignment 10, question 5. Can you please discuss that?
Okay. So we'll take question one. Okay. Okay. So if the volume expansibility given as alpha equal to 1 by v dv dt, then the ratio of adiabatic to isobaric volume expansibility alpha is alpha b. Okay. Hmm. So this question is like, let's think about this question. So alpha is given, alpha is equal to 1 by v del v del t. Okay. And it's saying that the ratio of adiabatic to isobaric volume. So adiabatic is basically, so here adiabatic means alpha s. So this would be 1 by v del t at constant entropy s, and alpha p would be 1 by v del t at constant p. Okay. So now, like, there should be some relation between these two things, adiabatic and isobaric volume expansion. That is, that needs to be find out. Okay. Mm, okay, so okay, I'll think about this problem. Okay, there might be some relation between this. Okay.
Yes, I actually checked. It was CP by CV. I used that to solve this, but then the answer is not matching. That's why I'm asking you.
Okay. So answer is the answers are like uh, the options are not correct. That means you are saying, right?
Yes, like I was using the formula alpha S by alpha P equal to CV by CP, but then my answer is coming 0.84, but all the options are in -5 or around that.
Hmm. You are using this formula alpha S by alpha P equal to what is the relation you told? CP by CV.
CV by CP.
CV by CP. Is this the
Yes, yes.
correct relation?
Actually, I'm not sure. I asked AI and AI gave me this, so I'm not sure about the derivation.
Okay, so I will actually first have to check whether this relation is correct or not. Okay, so I will check this problem because in somehow this thing like using some maybe some relation from Maxwell's relation to write this thing in terms of maybe some CP or CV. Okay, this
Okay,
thing you have to I have to find out actually. Okay.
okay,
Hmm. Okay. This thing I have to find out. CP by CV. Okay. You have to use some relation from Maxwell's relation. Okay, I will check it. First of all, I have to check whether this is some other relation may be there. I will look into this problem. Okay. This question week 10 assignment 5. Okay. I'll check this problem. Okay. Okay, anyway. So okay, so in the last class we started our discussion from the Maxwell's relation. So uh, that you already know. Okay. SPT, this is the usual way to remember the Maxwell relation. So this is a diagram you can say to remember the Maxwell relation. So the relation is like this: del S, del S, del V at constant will be del P, del T at constant V, del T, del V at constant S will be del P, del S at constant V. There will be minus sign when you are moving from here to here. Okay. Next is del T, del P at constant S will be equal to del V, del S at constant P, and last is del S, del P. Del S, del P at constant T will be equal to minus del V, del T at constant P. Okay. So these are the like the important Maxwell relations. Okay. Next we discuss about the TDS equations. Okay. So there are three TDS equations are there. TDS equations. So so the first equation consider is as a function of, so there are three thermodynamic coordinates are there, E, V and T. So two of them you have to take as an independent coordinate. Any two of them you can take. So first case we consider the entropy as a function of T and V. So that means T and V are the independent coordinates. So by taking that at independent coordinates, you can write the first TDS equation that looks like this: TDS equal to CB dt plus T into del P del T at constant V into dV. Second relation, for the second relation you have to take entropy as a function of temperature and pressure. T and P are we are taking as an independent coordinate. In that case, the TdS equation will be TdS equal to Cp dt minus Tv alpha dP. And third relation is where you have to take the entropy as a function of P, pressure and volume, and if you do that, you get TdS equal to Cp del T del V at constant dV plus Cv del T del P at constant V dV. Okay. So these are the three TdS equations that we have discussed. Next, we have discussed the energy equations. Okay, so these are very important equations actually. So energy equations. So the energy equation. So energy equation basically gives you this equation basically gives you a way to directly compute the internal energy of the system. Uh, internal energy of the system directly from any thermodynamic coordinate. So you, for any system, you can easily measure the pressure, temperature, and from there itself you can calculate its internal energy. Okay, U, using this energy equation. So this energy equation starts from the second law of thermodynamics, T equal to TdS minus PdV. So by rearranging some terms and doing some algebra, you will get the energy equation like this: del U del V at constant T would be equal to T into del P del T at constant V minus P. Okay, this is the energy equation. Now using this energy equation for like what you can do, you can for ideal gas PV, you know, ideal equation equal to PV equal to PV equal to nRT. So you can write P as nRT by V, and from there you can substitute this thing here, and by substituting it you can get the expression of the internal energy for an ideal gas. Similarly, for a real gas also, you can know the real gas is the obeys the van der Waals equation. So that equation looks like this. So this equation also, if you substitute here, you will get what is the expression of the internal energy for a real gas. Okay. Using this, basically this shows the significance of the you can say this energy equation. Okay. So from like any, if you know the gas equation of any kind of gas or any fluid, so by substituting that equation you can get its internal energy using this energy equation. Next is the, so next we have expressed Cp and Cv in terms of standard thermodynamic coordinates like P, V and T. So Cp initially we know is T into del S del T at constant P. So this thing you can write it as T into del P del T at constant S into del V del T at constant P. Okay, so these relations may be used to solve that problem, right? This expression of Cp and Cv. Okay, that problem they have that assignment 10 question number 5. Okay, you can see the
Yes, yes.
CPCV can be write in terms of del P del T del V del T in terms of constant entropy and pressure. Maybe I have to check this one. Okay.
Okay, okay.
Yeah. Similarly, CV also you can write it like this: minus T. The CV expression is T into del S del T at constant V. You can rewrite it as uh, minus T del V del T at constant S into del P del T at constant V. Okay. Yeah. Next we have discussed the relation between the Cp minus Cv. Okay. Uh, yeah. So we started from entropy as a function of T comma V, and from there we have to write down the one of the the difference between Cp minus Cv. So Cp minus Cv, you can rewrite it as like this. So Cp minus Cv equal to minus T del T at constant V whole square into del P at constant T. Okay. Also, you can expand this thing, you can write in terms of alpha and kt. Okay, so that would be tv into alpha square by kt, where you know alpha is 1 by v del t at constant p, and kt is minus 1 by v del p at constant t. Okay. Okay. Next, we have discussed about different types of thermodynamic coordinates, right? So first is the enthalpy H equal to U plus PV. This is enthalpy. Next is the Helmholtz free energy or free energy, that is given by F equal to U minus Ts. Next we have discussed about Gibbs free energy. So Gibbs free energy, that expression is given by G equal to U plus PV minus Ts. Okay, so these are the different types of thermodynamic functions that are useful, right? And also we have discussed about the Gibbs-Helmholtz relation. Gibbs-Helmholtz relation, that is given by, so there are two relations basically, U equal to F minus T into del F del T at constant V, and H equal to G minus T into del G del T at constant V. So basically you write the internal energy U as a function of Helmholtz free energy and enthalpy as a function of Gibbs free energy. Okay. Using this Gibbs-Helmholtz relation. Okay. Yeah. These are the pretty much important things that we have discussed in the last class, and also we have also discussed for like different condition, what are the thermodynamic functions that are remain zero, or that goes to maxima or minima. Okay, like for we have discussed like for adiabatic and isoporic process, we discussed that du should be less than 0. So that means u should be the minima, you should reach minima. So in order to happen this process, any kind of adiabatic isobaric process, the internal energy of the system should reach the minimum in order to occur that process. Okay. Similarly, for adiabatic and isobaric process, we discussed that BH, the enthalpy should reach minimum. Okay. For isothermal and isoporic process, the dF should be less than 0. So free energy should reach minima. And lastly, for isothermal and isobaric, the dG should less than 0. So Gibbs free energy should reach minima. these are basically the conditions to basically to spontaneously occur those kind of systems, so those kind of processes. Okay. So today's class will be discussing more on like more about the phase transition. Okay, so yeah, so we know that phase transition. Phase transition means like the matter is evolving from one phase to another phase. Okay, so phases means like in normal material we have like a solid phase, liquid phase, and gas phase. Okay. Apart from these phases, there are also other phases also. Like in condensed matter, there are like crystalline phase. Okay, crystalline phase, ordered phase, disordered phase. Okay, there are many kind of phases are there. Okay. So in order to basically characterize all these phases, there are certain kind of parameters and also certain kind of phase diagrams are there. Okay, so like if you vary those parameters, how by changing like what is the critical value of that parameter that is required to evolve the system from one phase to another phase. So in order to know that, you have to first draw the phase diagram of the system. Okay, so from the phase diagram you can actually calculate like what is the critical parameter value that is required to cause this phase transition. Okay, so here like so phase transition like let's suppose there is a in a beaker there are some water is there. So if you using some heater or something at a temperature T, if you hot this water, so it will boil and there is some vapor will be there, and that would be a phase coexistence. Okay, so there is two kind of phases that coexist with each other. So one is the vapor phase of water and one is the liquid phase of water. Okay, at particular temperature T. So this the reason that these two phases coexist, that means that at this particular temperature, these two phases uh, reach equilibrium. Okay, that is the reason these two phases coexist inside this container. Okay, at a fixed temperature T. Okay, at fixed T. Now, if you change this temperature, there will be there will be a different kind of equilibrium will be there. Okay, the equilibrium basically the region of the equilibrium will get changed, and we will get a new point of equilibrium if you change the temperature. Okay, so for a fixed temperature, there will be a fixed equilibrium. Okay, where like all the pressure and everything will be equal. Pressure gives free energy. All these things will be equal. Okay. So now, so let's suppose. Okay, so in order to see what kind of thermodynamic functions that are remain fixed during this phase transition, you have to basically consider what type of system is this. Okay, if it's a let's suppose it's an isothermal and isobaric system. Okay, since we are keeping the temperature T as fixed and also inside this container the pressure is also fixed. This pressure is known as uh, saturated vapor pressure. Okay, saturated vapor pressure. So that means this pressure is constant, temperature is constant. So this you can consider it as a isothermal isobaric process. Okay. So we already discussed in case of an isothermal isobaric process, the change in Gibbs free energy should be equal to 0. Okay, that is the condition for the equilibrium. Okay, condition for equilibrium. Okay. So when when the if you see the Gibbs change in Gibbs free energy in the system is become equal to zero, since the Gibbs free energy first tries to minimize itself, and after when it reaches the equilibrium, the change in Gibbs free energy should become equal to zero. Okay. Yeah. So if you write so d is equal to zero, that means you can write it is like that. So G is basically NL into GL plus NV into GV. So NL is basically number of moles in the liquid phase, and GL is Gibbs free energy per mole. Similarly, V is number of moles for vapor phase, and GV is the Gibbs free energy per mole. So Vg is equal to 0. You can write from here equal to GL equal to GV. Okay. This is the condition for the uh, equilibrium for an iso, like for this kind of a system where two phase, like phase 1 and phase 2 coexist for an one component system. Okay. So uh, equilibrium condition for a single component system. Single component means, since here water is only one component, so the vapor is basically one is the gas form of the water, and liquid is like the liquid form of the water, right? So in that way there is just a single component is there, so that's why it's called a single component system. Yeah. Similarly, for like solid liquid, if the system contains solid liquid or solid vapor or liquid vapor, all of the cases, this should be the condition for the equilibrium. Okay. For like solid, liquid, or solid vapor or liquid vapor. For all of the cases, for all of the single component cases, this should be the equilibrium conditions. Gibbs free energy of phase 1 should be Gibbs free energy of phase 1 should be equal to Gibbs free energy of phase 2. General condition. Next is the latent heat. Okay, so latent heat is like so when there is this phase transition is happening, let's suppose at particular parameter value, let's suppose it's a critical temperature, let's say. So at a particular critical temperature for water, we know that for like transition from solid to liquid or liquid to solid, for water the transition temperature, you know, it's 0 degree centigrade or 273 Kelvin. So that means at that particular temperature, so there is some heat that is basically used or required to make this phase transition. So that heat is basically known as the latent heat. Okay. Latent heat. That is heat required to change phase at fixed temperature. Okay. So yeah. So this latent heat expression you can directly write. So if let's suppose its system phase transition is happening from, let's suppose, phase 1 to phase 2. Let's suppose phase 1 has entropy S1 and phase 2 has entropy S2. So between this phase transition there is some heat, that is, let's suppose its exchanging is dq, so we know dq equal to tds. So for latent heat, instead of dq you can write it as L. Okay, so integration of dq you can write it as L. So this is the standard notation to specify the latent heat. So L is basically equal to T into S2 minus S1. Okay. Also, you can write the same equation in terms of entropy per molecule also. Okay, so latent heat per molecule L equal to T minus S2 minus S1. Okay. So this is the per unit molecule. Okay. Also, you can write the same relation in terms of molar latent heat also. So molar latent heat Lm is equal to T into S2m entropy per mole and S1 mole. Okay. So, and the relation between all of these different types of latent heat is like this. So, Nm equal to Na into L. Na, let's suppose number of atoms, number of molecules. So, that into L would be ml by 100. Okay. This is in SI unit, in SI, and CGS it would be ml in CG. Sorry, it would be 1000. Since latent heat is joule per kg, okay. Standard units are this normal latent heat. Here its unit are joule per kg. Okay. So if you convert it into the mole, so you have to basically convert a kg into gram. Okay. Yeah. Okay. So now, as we have discussed, so next thing that will be discussed, that we have discussed that in order to visualize this phase transition, okay, what we need, we basically need a phase diagram. Okay, like using this thermodynamic coordinates like pressure, temperature, volume, we have to form some kind of a phase diagram to basically characterize what is like the critical temperature or critical pressure that is required to make this phase transition happen. Okay. So for that reason, initially there is a equation that is known as the Clapeyron's equation that has been proposed to basically characterize this, or to get an idea about this phase transition plots, okay, or phase transition diagram. So let's first discuss about the Clapeyron's equation. There is also another equation called Clausius-Clapeyron's equation, that is a bit different thing. So first we will discuss about the Clapeyron's equation. So okay, so Clapeyron's equation is like this. So uh, the phase transition diagram looks like this. Okay, so let's suppose we have two independent coordinates, pressure and temperature. So you have to write a phase transition diagram like this, where the Gibbs free energy will remain constant. Okay, be like along this line. Okay. So like this point G2 is equal to G1. Okay. This is the phase transition line. Okay. So in this line, this point where two phases basically coexist, any of this point, the Gibbs free energy of phase 1 should be the Gibbs free energy of phase 2. Okay. So now, so what happens? So let's suppose you like this is, let's suppose at a particular temperature T and particular pressure P, you got some equilibrium conditions, so G2 equal to G1. Okay. Now, if you change the temperature from T to T plus dt, so in order to like so their equilibrium also gets shifted, right? So pressure will also get changed. P equal to P plus dP. Okay. in order to keep the system into equilibrium. So from T to delta T, if you change T plus delta T, pressure will also change from T plus delta P. Okay. So a new equilibrium will form at this point. Okay. So at this new equilibrium point, the Gibbs free energy also will change. So G2 will become so the Gibbs free energy at phase 2 will become G2 plus DG2, and Gibbs free energy at phase 1 become G1 plus DG1. Okay. So at equilibrium, we know this G1 plus DG1 will be equal to G2 plus DG2. Okay. So from here you can write DG1 equal to DG2. And after doing some algebra, you know G is basically, you can write G dg as v dp minus s dt, and if you substitute this thing here and after doing some algebra, you get this kind of equation: dp by dt equal to L, that is a specific heat, by T into V2 minus V1. Okay. So, so this is basically known as the Clapeyron's equation. Okay. Clapeyron's equation. So the things, so here V2 and V1 is, so V2 and V1 is nothing but the specific volume. Okay. Specific volume of phase 1 and phase 2. Okay. V2 is for phase 2 and V1 is for phase 1. Okay. So that means if you know the difference between the specific volume between two phases and the required latent heat, so from that you can basically draw this phase diagram. Okay, by calculating L and V2 minus V1 for any kind of phase transition. Okay, for any kind of material, you calculate from there itself. You can basically draw their phase diagram in a PT diagram. Okay, in a PT plot. Okay. Next, we'll discuss about the integral form of this equation. Okay, so integral form. So, uh, so, so let's suppose a transition from liquid to vapor phase and vapor to liquid phase is happening. Okay. So, actually, what happens is specific volume at vapor phase, so V at vapor is much higher than the V of liquid. Okay. So when basically water becomes from liquid to vapor, its total specific volume gets much increased from its liquid form. Okay. Now if you take this condition for this Clapeyron's equation, if you basically put that condition in the Clapeyron's equation, the equation becomes like this: dp dt equal to L minus T into V vapor. Since the liquid, the value of the V liquid is much smaller, so you can ignore that thing. So now from the, if you, let's suppose this kind of gas is there, it's basically kind of an ideal gas. If you consider it as an ideal gas, then it would be PV equal to RT. Now from here V equal to, right, RT by P. Now the specific volume, if you write in terms of specific volume, the specific volume as a form of normal volume, so that would be V vapor, that is a specific volume, would be equal to normal volume by mass into 10 to the power minus 3. So it will become RT by PM into 10 to the power 3. Okay. The equation will become dP by dt equal to L by T into Pm by RT into 10 to the power 3. Okay. So from here, you can write dt by P equal to L M by R into dt by T square. Okay. Now, from here, if you integrate, you will get ln P equal to minus Lm. Lm means molar specific heat. Okay, Lm by RT plus some constant. So this graph basically tells you how is the, if you plot this graph in a P and T diagram. Okay, so by plotting this graph, you will get some kind of a phase diagram kind of a thing. Okay, for a case of an ideal gas. Okay. And this law is known as Young's law. Young's law. This is one of the integral form of the Clapeyron's equation. There is also another form. There you have to consider that the specific heat of specific heat as a function of temperature. If you plot the specific heat as a function of temperature, experimentally it has find out that it follows a linear kind of a relation of A plus BT. Okay. Now, if you substitute this thing, Lm equal to A plus Bt, in this relation here, you will get dP by dt equal to A plus Bt by RT squared into P. Now, from a similar way, if you do dP by P equal to, you can write it as A by RT squared into dt plus B by RT into dt. But if you do integrate, you'll get ln P equal to K into ln T minus mt plus some constant B. So this relation is known as the Kirchhoff law. Okay, this is known as Kirchhoff's law. Previous one is known as Young's law. This is known as Kirchhoff's law. And this results is also very much consistent with any kind of experimental results. So, like this equation is consistent with very many experimental results also. Okay. These are the two important relations. Then one is this Young's law, and next is the Kirchhoff's law. These are nothing but integral form of this Clapeyron's equation for a basically a simplified case. Okay. I will discuss about the phase diagram, like phase transition. Okay, phase transition. So basically categorize this phase transition into two types. Okay, one is type 1 phase transition and one is type 2 phase transition. So first we'll discuss the type 1 phase transition. So mostly the things that we see like this water melting or any kind of material that is melting or freezes or become boiled to condensation, sublimations. So all of this phase transition processes comes under the first order phase transition. Okay. And the second order phase transition basically comes from like when you cool down any material like any metal too much in a too much low temperature. So in that case, that material becomes from normal conductor state to superconductor state. Okay. So these kind of phase transition are basically known as second type of phase transition. Okay. So in that case, the physics are a bit different. Okay. So normally this phase transition like this melting, boiling, condensation, sublimation, this comes under first order phase transition. Okay. So why it is known as first order phase transition? So, okay, so the reason is that uh, if you plot the entropy and the volume as a function of temperature, so let me first write. Okay. Let me first write first order phase transition. The example consists is like melting, freezing, uh, sublimation, boiling, condensation. All these processes are basically comes under first order phase transition. Okay. And they are like termed as first order phase transition because the entropy, there is a discontinuity into the entropy and the volume, specific volume of during this phase transition. Okay, so entropy and volume, this functions changes discontinuously across these transitions. Okay. And the first order, the reason for the first order term is that this entropy you can write as a function of Gibbs free energy. Okay. S is equal to minus del T at constant P, and D, the specific volume, is del G, sorry, del G del P at constant T. So this first derivative of this first derivative with respect to the temperature and pressure of Gibbs free energy basically remains shows a discontinuity during the phase transition. Okay, so that's why it's known as the first order phase transition. So similarly, for the case of second order phase transition, what will happen? The second derivative of Gibbs free energy shows some discontinuity. Okay, but for the first order phase transition, what happens to the second order derivative of this Gibbs free energy? Like specific heat. So specific heat, you know, is T into del S del T. Okay, so that means it is a second derivative, right? It will become S into del square G del T square. So this is the second derivative of Gibbs free energy. So this will show a discontinuity. Okay, no, sorry, not discontinuity. It will diverge actually during the phase transition. At transition point, the second derivative of Gibbs free energy diverges. Okay, diverges means it tends towards infinite. Okay. So all of the quantities that are basically associated with second order derivative of Gibbs free energy during first order phase transition, those quantity will diverge at the transition points. Okay. So in terms of diagram, PT diagram, in GT diagram, how it will look like? So GT will remain continuous, Gibbs free energy, you know. G, if you plot GT, so it will so if this is the point where the transition is happening at this point, temperature point. So uh, so when the Gibbs free energy changes from phase 1 to phase 2, it will so now discontinue. It will just change from like this. Okay, phase 1 to phase 2. It's remain continuous. Okay. Now if you plot the entropy and or volume, let's suppose if we plot the entropy or volume, that is the second derivative of Gibbs free energy, it will show discontinuity. Discontinuity means like this. So you can see there is a jump from this point to this point. Okay, so from this point to this point, there is a jump. So that means there is a discontinuity exists. Okay, because of the phase transition here. Yeah, so since S and B are the first derivative of Gibbs energy, so during the phase transition point, it will show this discontinuity. Okay, so that means just a jump, you can say. And if you plot the specific heat, that is C, which is basically related with the second derivative of Gibbs energy, if you plot it, C is basically proportional to L square G, then T square. Okay. If you plot it with respect to T at this transition point, it will basically diverge. Okay, it will diverge like this. It will go like this and it will then diverge at this critical temperature value. Okay, phase 1 to phase 2. This is basically the characteristics of first order phase transition. So any phase transition, if you see, first you have to draw their diagram. That means from the diagram itself, GT diagram, SVT diagram, or this specific heat versus time diagram. So from this diagram, by plotting this diagram, you can basically characterize what kind of phase transition is happening there. Okay. Whether it's first order or whether it can be second order. Okay. Now, so okay. So now we'll check, say, like how using this Clapeyron's equation, okay, and by calculating this different quantities like specific heat and change in specific volume, how you can construct the phase diagram, that we will check. Okay. So you know the Clapeyron's equation looks like the dP by dt equal to L by T into V2 minus V order. Okay. Now, so basically what we need the information of L and information of delta V, that means the change in specific heat, in order to get a rough estimation of this phase diagram. Okay. So there are three different types of transitions are there. One is solid to liquid. From solid to liquid, it will be melting. From liquid to solid, it will be freezing, right? Same way. From liquid to vapor, it will be boiling, and from vapor to liquid, it will be condensation. Okay. And lastly, it can also there are some materials, if you heat those materials, that can directly turn from solid state to directly to gas state. Okay. So solid to vapor. Solid to vapor, the process is known as sublimation. Sublimation. And to vapor to solid with solidification. Right. So, so if you calculate the change in specific heat for all these processes, let's suppose for melting, the change is delta Vm. For boiling, this change is delta V, and for sublimation, let's suppose the change in delta Vs. Okay. Now, if you compare their values, you will see the value of delta Vb is comparable to the value of delta Vs, but the value of delta Vs is much greater than the value of delta Vn. So in this, that means from this relation, Clapeyron's equation, you can see what that means for del P del T dP dt at melting point. For melting point, since del Vm is smaller, so del P del T will be much higher than del P del T for the case of sublimation and for the case of boiling. Okay. So that means this in the PT diagram, the slope of the P, so slope of this phase diagram, or this yeah, constant phase diagram. If you draw their phase diagram, the slope for the process of melting, the slope of the phase diagram will be much steeper than the phase diagram for sublimation, for the case of sublimation and boiling, right? So it would looks like this. Rough estimated picture, it looks like this. So this is P and T. We know for the case of melting and freezing, this slope is steeper, so it will looks like this. For the case of sublimation and boiling, the values are a bit comparable, so it will looks like this. So this curve basically separate out uh, solid and liquid phase, right? This curve is basically separating out liquid, solid, and vapor, and this phase is separated out liquid and vapor. Okay, so it looks like kind of this. Okay, so if it moves from solid liquid to solid, it will become freezing, and from solid to liquid, it will become melting. Similarly, from solid to vapor, it will call sublimation, and vapor to solid, it will call solidification. Similarly, from liquid to vapor, it will called as boiling. Yeah, and vapor to liquid, it is known as condensation. Okay. This is how a typical phase diagram looks like. Now, if you connected this point, it will looks like this. All the lines connected, it looks like this. So this middle point is the known as the critical point. Okay, but all of these three phases coexist with each other. Okay, critical points. So at this point, basically, for any kind of gas or fluid, if you make the system, if that system has three phases, and if you put the system at this critical point, at this particular critical pressure and temperature value, then all of the three phases that is possible for that system basically coexist with each other. Okay, this is the known, sorry, not, it's not critical actually, it's known as triple point. Okay, not critical point, it's known as triple point. Okay, all the three phases coexist. Okay, all three phases all three phases coexist. Okay, this is known as the triple point. Critical point is actually here. This is the critical point. Okay, we have discussed what is the significance of this critical point, right? PC, VC, and PC. Okay. As we have discussed at triple point, all the three phases coexist. So G solid will be equal to G liquid, G liquid will be equal to G vapor, and G vapor will be equal to G solid. Okay. Solid, since solid, vapor, and liquid three phases coexist with each other, so this is the condition of coexistence. Like the Gibbs energy for each of the phases should be equal to each other. From this three relation, you can write this formula. Okay, so L SV is equal to L SL plus L LV. Okay, so L SB means latent heat to change the system for solid to vapor. Okay, similarly here, latent heat for solid to liquid, and this is latent heat for from liquid to vapor. So that means the latent heat that is required to do phase transition of solid to liquid and liquid to vapor. So both of these Latent heat is the addition is basically equal to the latent heat that is required to phase transition from solid to vapor. Okay. This is an important relation. Okay. This only happens at triple point only. Okay. This only this phenomena or this relation only is true when the system is in triple point. Okay. Okay. So far we have discussed about the process equations. Now there is another type of equation which also basically characterize this phase transition, and that equation is known as Clausius-Clapeyron's equation. So for the for the case of Clapeyron's equation, we have considered the latent heat as a fixed thing. Okay, that has a constant value during the phase transition. It has a constant value, but if you consider that latent heat is also a function of a variation of temperature. So if the latent heat is also change with temperature, so in that case, how it can be written out? Okay, how can that particular equation can be modified? So initial equation you know is like SF to SI, the change in entropy of initial to final. SF minus is equal to L, that is the change in that is a heat, latent heat that is exchanging during the phase transition by T at this particular point. Now if you do temperature derivative, it will become del SF by del T minus del SI by del T equal to del L del T minus L by T. So if we simplify this thing a bit, it will become del L del T equal to L by T. Okay, so now what we can do now here, yeah, so it will become del L del T equal to, okay, there is a T sign there, okay, there is a T here, okay. Now it's fine. So del L del T will be equal to L by T plus, so T into del SF by del T. You can write it as specific heat at final case at a fixed saturated pressure. For a fixed saturated pressure, let's write it as PSO. Specific heat at fixed saturated pressure. At for the final state, so you can write it as CF at constant PS minus CI at constant PS. Okay. This is the general form of how latent heat is changing with temperature, and this is known as the Clausius-Clapeyron's equation. So good. Now instead writing the specific heat as specific heat at constant saturated pressure, you can also write it in a more familiar way at constant normal pressure. Okay, so in that case this expression will become a bit modified. Okay, in that case it will become del L del T will be equal to L by T plus Ci constant P minus, sorry, CF at constant P minus CI at constant P minus n into Vf minus Vi into del Vf del T at constant P minus del Vi del T at constant P. Okay, these equations are known as basically Clausius-Clapeyron's equations. Okay. Okay. Now next will be discussed about the Gibbs phase rule. Okay. So what does this Gibbs phase rule tells us? This tells us about the rule is very simple. We have discussed about, like initially we discussed about one component system, two component system. So let's suppose, or we will also discuss for a one component system that three kinds of phases are possible: vapor, liquid, and solid, right? So instead of one component, let's suppose P component, C component systems are there, and for that system, P numbers of phases as possible. Okay. And let's consider the system as a closed system with fixed temperature and pressure. So it's basically isothermal and isobaric system. Okay. So in that case, what is the number of independent intensive variable that is required to basically characterize the system? Okay. So that is related with the number of components and number of phases. Okay. So you'll write that relation. Okay. So consider uh, closed system with fixed T and P open. And let's suppose the system has C components and P number of phases. So in that case, the number of intensive variable, number of maximum intensive variables is given by F equal to C minus P plus 2P. This is the Gibbs phase rule. For a single component system, uh, equal to 1. Uh, the lowest value that is required, if it is 0, in that case the P would be equal to 3. So that means maximum lowest, if we take the lowest value of F, in that case the maximum value of phases. Okay. Maximum value of phases that is possible is 3 phases. Okay. This you got from this Gibbs phase rule. Okay. Now, lastly, we'll discuss a deep about uh, the second order phase transition. Okay, so for the case of first order phase transition, we know this clauses. So to characterize this, the phase diagram and all, we basically need the Clausius-Clapeyron's equation or Clausius-Clapeyron's equations, and you know that the Gibbs, for case of first order phase transition, the Gibbs free energy remains continuous. The first order derivative of Gibbs free energy gives discontinuity, and the second order derivative of Gibbs free energy diverges at the critical point. Okay. So that was so far the primary properties of first order phase transition. Okay. But in the case of second order phase transition, the things will be a bit different. So here you cannot use the Clausius-Clapeyron's equation, right? So here you have to use a different types of equation that is known as the unphased equation, that also we'll see. And uh, also the different thermodynamic like the Gibbs free energy, the second order Gibbs free up to the second order Gibbs free energy, the discontinuity will be there also. Okay. So those quantities will also play a very important role to basically formulate this unphased equation. So let's write it as second order phase transition. Some of the examples of the second order phase transition is in the magnetic material. If there is a ferromagnetic material is there. If you heat up that ferromagnetic material, then it's basically the ferromagnetism got reduced with temperature. Okay. Now after a certain temperature, there is some transition is happening from ferromagnetism to paramagnetism. Okay, where basically all the magnetic moments are randomly distributed. So that particular critical temperature is known as the Curie temperature. That is basically denoted as TC or Curie temperature. Okay. So that transition is a kind of example of a second order phase transition. Okay. So first is the ferromagnet to paramagnet, or opposite thing can also happen from paramagnet to ferromagnet at Curie temperature. Second example is from material, any kind of material. So like there are only certain kind of material which can show the superconductivity property. So material to superconductivity. If you basically decrease the temperature where the material is, decrease lower, very lower. If you make T very smaller, in that case the material can turn into a superconducting material. Okay. At lower temperature TC. This is also example of second order phase transition. So the properties of the second order phase transition, we already know that Gibbs free energy remains the Gibbs free energy remains fixed. So G1, that is the Gibbs free energy at phase 1, is equal to Gibbs free energy at phase 2. The second property is the second derivative of Gibbs free energy, that is given by the entropy. Entropy at phase 1 should be equal to as entropy at phase 2. Similarly, the specific volume at 1 will be equal to specific volume at 2, phase 2. So these are some certain properties of of the second order phase transition. Okay. Now using this property, okay, we can basically derive these unfazed equations. Okay, so we start from let's start from this one. Okay, so S1 that entropy is a function of temperature and pressure. Okay. So S1 is basically T comma P equal to S2 at T comma P. Now from here, if you do a small variation, ds1 equal to ds2, and by using the total derivative of ds1 in terms of temperature, pressure, and using some Maxwell relations, you will end up by this relation. Okay. Cp at phase 1 will be minus of Cp at phase 2 into T will equal to minus Tv equal to alpha 2 minus alpha 1. Alpha 2 alpha 1 is basically the volume expansivity at phase 2 and phase 1 into dp, or you can write it like this also, dp by dt equal to cp2 minus cp1 divided by tv divided by alpha 2 minus alpha 1. So this is a form of an unfazed equation. Okay. Here, as you can see, this equation is written in terms of Cp and Cv. So Cp and Cv are basically double derivative of the Gibbs free energy. Okay. So that means since for the second order phase transition, the double derivative of Gibbs free energy, so some discontinuity, so that can be measurable. Okay, so from that value of discontinuity, we can basically calculate the Cp2 minus Cp1 thing, and from there itself you can calculate its what is the slope of this of the phase diagram of this kind of second order processes. Okay, so there is another form of this unfazed equation. For that form you have to consider the volume. Okay, so volume also remain constant. So just like the for the case of the entropy we have done, similarly for the case of volume, if you do uh, you have to write it like this, dv1 equal to dv2, and v you can take as a function of pressure and temperature. Similarly, if you take the total derivative and using some Maxwell relation, you will be getting the equation like this: dp by dt at constant volume will be equal to alpha 2 minus alpha 1 by kt 2 minus kt 1. Where just for sake we are writing kt is nothing but this quantity, compressibility basically 1 by v del v by del p at constant t, and alpha we know is 1 by v del v by del t at constant t. So this is also a form of form of the unfazed equation. As you can see, this alpha and kt also is also a first derivative of volume. That means the second derivative of Gibbs free energy. Okay, so that means these quantities also will show in the PT diagram or PV diagram. It will show some kind of a discontinuity during the phase transition for the case of second order phase transition. From the discontinuity, you can easily calculate this slope dp/dt, okay, for the phase diagram. Okay. Okay, now let's done some problem. Okay. Problem one is the equilibrium vapor pressure P of water as a function of temperature is given. So there is a table given where how this vapor pressure is changing with temperature for water. So it's the table looks like this. One is T axis and P axis. So T is 0, all are on degree centigrade, and pressure is in Pascal. 0, 10, 20, 30, 40, 50, and the corresponding pressures are 611, 1228, 2339, 4246, 7384, and 12349. So now okay. Okay, so how to do that? So in order to do that, we already know that. So okay, so the problem is like if this table is given, so in that case you have to deduce the value of heat of evaporation, latent heat of evaporation, latent heat of evaporation, that they are denoted as LV at 25 degrees centigrade. Okay, 25 degrees centigrade. So for that we know we need the phase diagram, right? So in order to get the phase diagram, what you need the Clapeyron's equation. Clapeyron's equation is this dp by dt equal to L by T into delta V, right? Now you can write, so we're considering it as a uh, we are considering it as a ideal gas. In that case, we can write this thing as like this. So it's basically melting from uh, heat of evaporation. So from liquid, it's melting from liquid to vapor, right? So we know the VL is, and if it's V, this V vapor, sorry, this is the specific heat at vapor and specific volume at liquid. You know, the specific heat for case of vapor is much higher than the specific heat for the case of liquid. So it would be, that means L would be T into V vapor, right? And you already know PV equal to nRT. We consider it as an ideal gas. So V you can write as nRT by P. So we substitute this thing here, so you'll get L into T into nRT square. That is equal to dp by dt equal to this. Now if you arrange all the variables, dp by p equal to dt by t square into L into nr So the relation will become ln T minus L into nRT plus some constant B. Okay. So that means if you basically if you have points, so at temperature and pressure, okay, and this is the equation of your phase diagram. Okay. So if you basically plot ln T in the y-axis ln T and 1 by T as x-axis, in that case the curve will be a linear curve like this, right? And the slope of the linear curve will be minus L into NR, right? So this will be the slope. So that means if you calculate the slope of this particular curve, from that itself you can easily calculate the latent heat by so L would be, that means equal to minus NR into the slope, right? So now, so we are so here. So that means you have to write these points, the points that are given here, as a function of ln p and 1 by t. So if you write it as 1 by t as x-axis and ln p as y-axis, if you convert these points that is given in the problem, it will become into 10 to the power 3, let's suppose 3.633, 3.533, 3.413, 3.3, 3.195, similarly 6.415, 7.113, 7.757, 8.907, 9.421. Now these points are given. Now if you know the coordinates of those 2 points, like let's suppose this is x1 y1, sorry x2 y2, and this is at x1 y1. Now if there is a straight line connecting between these 2 points, so in order to calculate its slope, we know the slope formula is this: slope is equal to y2 minus y1 divided by x2 minus x1, right? Similar way, for this case also you can calculate the slopes. You have information of all of the points, right? So you can easily calculate the slopes by using this formula. Okay. So the slopes will be like this. Slopes will also minus 10 to the power plus 3. Since x2 and x2 minus x1 will go to the denominator, so it will be balanced by minus 5.369 minus 5.367 minus 5.283 minus 5.267 minus 5.192. So slopes you can see vary a bit. So what you can do, you can take the average of each of these slope. The average slope will give you minus 5.275 into 10 to the power 3. This would be the average of all these slopes. Okay. Now you got the slope. The formula is L equal to minus NR into the slope. So since it's 1 mole, so N equal to 1, R is 8.314. So the answer would be equal to minus plus 8.314 into 5.275 into 10 to the power 3. So it would be 42.9 into 10 to the power 3 joule per mole. So this would be the value of latent heat for evaporation. Okay. So this is how you have to solve this problem. You have to first find out what would be the phase line of this particular system that you can get from using the Clapeyron's equation. This is the Clapeyron's equation, and from this Clapeyron's equation, the phase line looks like this, where ln versus 1 by t follows a bit this linear kind of a diagram, and where the slope of this diagram is particularly related with the latent heat. So in order to calculate the slope, we have used the data that is given in the problem, and from there we have to calculate the slope, and from the slope we get the latent heat of evaporation. Okay. So the next problem we'll now discuss, so problem 2. The sublimation curve of solid NH3 is given by ln P equal to 23 minus 3750 by T, and the vaporization curve at liquid NH3 is ln P equal to 19.5 minus 3050 by T, where P in this unit and T in Kelvin unit. Okay. The answers are A is 200 Kelvin, B is 163 Kelvin, C is 156.4 Kelvin, and D is 700 Kelvin. Okay. The problem is the sublimation curve of NH3 is this, and the vaporization curve of NH3 is this. Okay. So, so you have to find the temperature of. So the problem is you have to find the temperature of triple point. Okay, so the T triple you have to find out. Okay. So in the phase diagram we know this is like it looks like, so we have already discussed, right? So this is how the diagram looks like. Okay, this is how the diagram looks like. Solid vapor and uh, solid vapor, this is sublimation curve. This one is the sublimation curve, solid and vapor, and next curve is the vaporization. That is means liquid to vapor, right? So this is the vaporization curve. Okay. So these two curves basically intersect in this triple point. Okay. So it looks like this. This is the sublimation curve, and this is the vaporization curve, which meets at the sublimation. This is the vaporization. Okay, it looks kind of like this. Vaporization. Vaporization. And this is the triple point. Okay. Where both this curve meets. Okay. So that means both of this equation will be equal at triple point, right? So at T trip 23 minus 3750 by T will be equal to 19.5 minus 3050 by T. So from here you can calculate the T is as 200 Kelvin. Okay. The correct option would be option A. So basically at a triple point where both these two curves basically intersect, at that triple point I have to calculate. Okay. Just you have to basically equate those two curves, and from there itself you can easily calculate a triple point. Okay. Problem number 3. Calculate the deflation in the melting point of ice by 1 atm by 1 atm increase of pressure. Okay, so basically increase the pressure by 1 atm. So in that case, uh, what will be the change in the melting point? Okay, because these things are triple this transition point, these are all related with each other, pressure and temperature. So if you change the pressure, the melting point of that particular system will also get changed. Okay. The given information is there. So given is, so it's a case for an ice actually. Okay, so given is latent heat of ice is given at L is at 3.4 into 10 to the power 5 joule per kg. Specific volume of 1 kg of ice. 1 kg of ice is ice and water is given at 0 degrees, given at 0 degree is given as 1.091 into 10 to the power minus 3 meter cube and 1 into 10 to the power minus 3 meter cube. Okay, so this is easy. So first so we have to basically, so the what we have to do here, so we have to start from the Clapeyron's equation, dt by dt equal to L by T into V2 minus V1 of 1. So this is basically dP denotes the small change in pressure, okay, and dt shows the uh, small change in temperature as due to dP, okay, due to dP. Okay, so that means if you change the pressure by P plus delta P, because of that the temperature will change T to T plus delta T. So here temperature is nothing but the melting temperature. So you can write it as dt will be equal to, that means T into V2 minus V1 by L into dP. Okay. So now everything is given. So dt is T is 273. V2 is basically this 1.091 into 10 to the power 3, 10 to the power minus 3. Yeah, it is minus 3. 10 to the power minus 3 minus 1 into 10 to the power minus 3. So this will give you minus 0.091 into 10 to the power minus 3 into dP, change in pressure, that is given in atm. So atm we have to convert into Pascal, so it will become 1.013 into 10 to the power 5 Pascal, and denominator it will be a specific heat. Specific heat is 3.4 into 10 to the power 5 joule per kg. So 3.4 into 10 to the power 5. So calculate this, dt will give you minus 0.007 Kelvin. So this would be the change in the melting point. Okay. If you change the pressure by amount 180. These things can be easily calculated by using the Clapeyron's equation. So the question 4. Calculate the change in boiling point of water. Similar type of problem. Point when the pressure changes, increased, you can say, increase by 1 atm to 2 atm. Okay. Specific volume of water and steam are given at 100 degree as so V specific heat of water is 1 cc by gram, and V at steam is 1601 cc by gram at 100 degree centigrade. Okay. And latent heat of steam is given as 2268 kilojoule per kg, and boiling point of water at 1 atm. So that we know, temperature of boiling water at 1 atm is given by 100 degree centigrade. So in this case, you have to you have to calculate the change in boiling point of water. So similar way, first write the Laplace equation dp by dt equal to L by T into V2 minus V1. Okay. So here change in temperature, so dt will be equal to T into V2 minus V1 by into dp by L. So T is, we know, is 100 degrees, so 373 into V2 minus V1 is 1601 and minus 1, so it would be 1600. Net pressure is 1 atm, so 1 point, so that we have to convert it in Pascal, so 1.013. dP is basically 2 minus 1 atm, right? It increased from 1 atm to 2 atm, so 2 minus 1, it would be 1 atm. So that is 1.013 into 10 to the power 6 Pascal, right? Divided by the specific heat, that is 540. Not 540, it's latent heat. Yeah, sorry, it's latent heat. Yeah, 2268. Yeah, 268. Kilojoule, so that means it will be a 10 to the power 3 is there. Okay. So if we calculate this thing, the dt will give you around 26.66 Kelvin. This is with the change in the boiling temperature. Okay. For the case of water, if you increase the pressure. The problem 5. Calculate the pressure required to lower the melting point of ice by 1 degree centigrade. The density of ice is the density of ice is 0.917 into 10 to the power 3 kg per meter cube, and latent heat of ice is 3.36 into 10 to the power 5 joule per kg. Okay. The options are option A 1.35 into 10 to the power 8. Option B, all are in Pascal. Okay. 2.49 into 10 to the power 7. Option C 1.36 into 10 to the power 7. And option D is 1.76 into 10 to the power 8. All are in Pascal. Okay. So So here the opposite thing of to calculate. Okay, so we have calculated dt by dt equal to L into T into V2 minus V1. Previously calculated dt, now here you have to calculate the dp. So dp is equal to L into dt by T into V2 minus V1. Okay. Since the change in melting point is given, so dt is basically 1 degree centigrade. Okay. Lowering, so that is it's minus 1 degree centigrade, so it's minus 1 degree centigrade dt. L we know L is given, so L is latent heat, so 3.36 into 10 to the power 5 joule per kg. The specific heat, the density of ice is density of water is V water, so V2 is the second phase V2, that is the water is 10 to the power minus 3 meter cube per kg, and for ice this is 0.917. 0.917. Okay, density is given. So its density is given. So the volume would be 1 kg for 1 kg of ice. The volume would be, that means 1 by 0.917. Yeah, 1.0917 meter cube by kg. Okay, that would be around 1.0905 meter cube per kg. Okay, V1. So now it's easy, just dp d1, so just you have to substitute value. So 3.36 into 10 to the power 5 into minus 1 divided by 273 into minus 0.0905 into 10 to the power minus 3. That would give you 1.36 into 10 to the power 7 pascals. This much amount change of pressure will be there. In order, like this much amount of change of pressure is required in order to bring down the melting temperature of ice by 1 degree centigrade. Next question is, which order of derivative of gives the energy is basically universe for a second order phase transition. Option is 1, option B is 2, option C is 3, option D is 4. So we know that for second order phase transition, the second order derivative of Gibbs free energy needs to be discontinuous, right? So the entropy, volume, all those quantities which are basically can be expressed as a second derivative of Gibbs free energy. So those quantities are basically so discontinuity. Okay, so the correct option would be option B. Next is problem 7. Gaussian Laron equation holds for option A, first order phase transition, option B it was second order phase transition, option C both A and B, and option D neither A nor B. Okay. So as you know, Clausius-Clapeyron's equations only hold for first order phase transition, that you already know, right? For second order phase transition, there is this unphased equation is there. Okay. So the correct option is option B. When L equal to A plus BT plus CT square, find the difference of specific heats of liquid and saturated vapor option A is Ct minus A by T, option B is At minus C by T, option C is Bt minus C by T, and option D is A by C by T square, A minus C by T square. So how to do that? So we know that from that there's a relation, the Clausius-Clapeyron's equation. So to use that equation, so from Clausius-Clapeyron's equation, you know, dl dt is basically c c2 minus c1 by minus L by T. Okay. So here the second phase is the so C2 the liquid, so C2 is Cl and C1 is C, it's the vapor to liquid, yeah, it's vapor. So specific and liquid is specific of liquid and saturated vapor. So these two differences you have to calculate, right? So Cl minus Cv is basically dl by dt minus L by T. Okay. So dl dt is basically d into d derivative of this quantity a plus bt plus ct square, a plus bt plus ct square. This is nothing but b plus 2ct, right? So we substitute this thing here, it will become B plus OCT minus L by T will become uh, A by T plus B, sorry, that will be minus B minus CT. Okay, so it will become CT minus A by T. CL minus CB. So the correct answer will be option A. So this is it. So this is our last problem. So today we have come to the end of our class. So if you have any doubt, you can ask. Or
No doubt, sir.
okay, so I'll then end the class now.